Other applications of electrochemistry. A list of what electrochemistry can be used for: batteries, hydrogen fuel cells, corrosion, corrosion prevention, and biology. Conventional batteries have an electrolyte, and then they have, for example here, they have a lead grid filled with spongy lead, that'll be the anode, and then a lead grid filled with lead dioxide, which will be the cathode. And you've got one battery here, another battery in series. Each one is 1.5 volts, so since they're in series, you add them, and they provide a total of 3 volts to this flashlight here. Alkaline batteries are a little different. They have your anode down here, the blue, the cathode up here is the red, and you have a separator between the two of them, and the outside will be negative, and the inside right here, that's going to be a positive. Hydrogen fuel cells have an anode and a cathode separated by a porous membrane here. You've got oxygen coming in, hydrogen coming in over here, then it exhausts hydrogen and also oxygen and water, generating a 1.23 volts. Here's the process we want to stop. We have a block of iron, we have water falling on it, and it's in the air, so there's oxygen. What's happening is the oxygen is acting as a cathode. Oxygen is being reduced to water, or it can be this equation too, where you have oxygen plus water, and that gets reduced to the hydroxide ion. That means that iron is the anode, and it's being oxidized. So we've got metallic iron turning into iron ion plus 2 electrons. And that goes off into this aqueous solution here, which forms rust, iron oxide with water. That's not a good scene. We're losing metallic iron. The way we defeat it is we take zinc. Now zinc has a higher negative electric potential than iron, so it becomes the anode, and it gets oxidized, and iron is now reduced. So we don't have iron forming iron ions. So we have the zinc coming up here, which means we lose the zinc material. At some point, this actually goes away by forming all these ions in the water, and iron stays protected. Rusting, and again, that's what's happening here on the previous slide with iron, that used to be the primary cause of cars needing to be discarded. Most cars had some rust after a few years. Now it's rare to see a rusted car being driven. To stop the rusting of ships, which are in one of the biggest electrolytes ever, right, seawater, sacrificial anodes are put along the hull, and that's these blocks here. This sets the ship up to be the cathode of the electrochemical reaction with seawater. The zinc blocks corrode away. They're sacrificed, but the hull is protected. And the zinc blocks are the light-colored rectangles, already said that. It's also used to protect docks, pipelines, any large outdoor structures. Sometimes additional circuitry is added to increase the protection. Another picture of it. Here is a block of zinc. And again, just reiterating, ship hulls made of steel are in an environment that causes severe corrosion. Salt water, barnacles, extreme temperatures. It's not cost-effective to make them out of stainless steel, which would resist rusting, and protective coatings don't last long. Right? You've got the barnacles eating them away, the ship's pounding on the water. So we've got the blocks of zinc. They will corrode, and they'll protect the hull from the galvanic reaction. The zinc is the anode, sacrificial anode, and the ship's hull is the cathode. The blocks do have to be replaced frequently as they are consumed by the reactions. Pipelines carrying oil and gas are subject to extreme weather that encourages corrosion, and protective coatings often fail or are damaged. Sacrificial anodes are not always able to be installed to protect the entire pipe run. Right, here's a pipe going on a long, long distance. A DC power supply supplies a current to prevent galvanic corrosion at key spots. The flow of electrons increases the cathodic reaction in the metal, thus reducing the anodic reaction, which destroys the metal.